Good afternoon. Fast work through the calculations for the vitamin C titration associated with the chemical analyst that you did a while ago. If you remember, you first of all took some vitamin C and you weighed it out and dissolved it up in 100 cubic centimeters. So I took 0.18 grams and dissolved it up. Then what we had to do was figure out how many moles of vitamin C we had, not just in that 100 cubic centimeters, but in each 10 cubic centimeters that we were going to take of that solution. So vitamin C had that structure, 6 carbons, 8 hydrogens, 6 oxygens in there, so that gave us a molar mass of 176.12 grams per mole. So 0.18 grams, divide that by 176.12 grams per mole. And that tells us we had 0.00102 moles of vitamin C, but that of course was in 100 cubic centimeters, so in each 10 cubic centimeters would be a tenth of that, or 0.000102 moles of vitamin C. So for this first part, every single titration we did started off with 0.000102 moles of vitamin C in the 10 cubic centimeters of solution. And if you remember, that was our analyte. That was what was in the Erlenmeyer flask, the conical flask. So then you did the titrations. So my rough titration was 17 cubic centimeters, and then I did the 3 more precise ones, 17.1, 16.8, and then 17.1 cubic centimeters. Okay, so I know the volume of the potassium iodate solution I had. I now need to know the concentration of that potassium iodate solution. Concentration is, of course, moles over volume of the solution. I got the volume of the solution, so now let's figure out how many moles that is. And of course, each 10 cubic centimeters of solution had 0.000102 moles of vitamin C in it. Now, the two equations that we use with this one, each mole of vitamin C needs 1 mole of iodine. So if I had 0.000102 moles of vitamin C, I'm going to need 0.000102 moles of iodine. And that iodine came from the potassium iodate solution that, of course, was mixed with potassium iodide and hydrochloric acid. Well, each iodate produces 3 iodines. So therefore, if I want 0.000102 moles of iodine, I only need 0.000102 moles divided by 3 moles of the potassium iodate. Okay? So therefore, each 0.00102 moles of vitamin C, so each titration, right, when I get to the end point, I would have added 0.0000340 moles of potassium iodate. Remembering, of course, concentration is moles per cubic decimeter. That's the standard way of doing it. So you see concentration without anything else given, it's going to be moles per cubic decimeter. So I need first of all to change these volumes to cubic decimeters. Well, that's easy. I just divide by 1,000. And now each one of these concentrations of KiO3, each one of these titrations, 0.00034 moles of KiO3 divided by the volume in cubic decimeters. Here that gave me 0.00199 moles per cubic decimeter. This one here dividing by 0.0168 instead of 0.0171 gave me 0.00202 moles per cubic decimeter, and this one was the same as the first one. So now average them out, and my average concentration of the KiO3 solution, 0.00200 moles per cubic decimeter. And a couple of you actually got that, or got very, very close to that. So that was the first part. And indeed, that was what I actually marked on, because it did take a little bit longer for some sessions to do this whole titration. But anyway, so the first part, getting the concentration, standardizing the potassium iodate solution is the fancy word for that, 0.00200 moles per cubic decimeter. Now the next part, we're going to take an unknown solid and figure out how much vitamin C was in that unknown solid. So my mass of unknown solid was 0.29 grams, and again I dissolved that up in 100 cubic centimeters, and so then I split that up again into 10 cubic centimeters of each of those. Now remembering the average concentration of potassium iodate solution was 0.00200 moles per cubic decimeter. Now let's do my titrations. So this one here, my rough one, 14 cubic centimeters. First precise one, 13.6 cubic centimeters. And remember, I'm now going to convert that all the way through to cubic decimeters to match up with my concentration. Next one, 13.8. Next one, 13.7 cubic centimeters, or 0.013 cubic decimeters. Now, one of the reasons I chose this titration was it's actually a really, really good one to get nice precise, so in other words all my values nice and close to each other, as well as accurate values of it. It's a nice titration because it's got that very, very clear end point when the solution turns blue, when you've got a little bit of residual iodine left over. And using starch, certainly the right amount of starch, is a very, very good endpoint determination. Anyway, here's my volume of the potassium iodate solution. And of course, I know the concentration of potassium iodate solution. So thus, for each of these titrations, I can get the moles of potassium iodate simply by multiplying that volume in cubic decimeters by the concentration, 0.00200 moles per cubic decimeter. So in each case, there's the moles of KiO3 that I had. Now, if you remember, every mole of KiO3 produces 3 moles of iodine. Each mole of iodine is sufficient for 1 mole of vitamin C. Therefore, to get the moles of vitamin C from the moles of potassium iodate, I just multiply by 3. And there's that. And then, of course, I know, once I know the moles of vitamin C, I know the molar mass of vitamin C is 176.12. So multiply these moles by 176.12 to get the grams of vitamin C in each of those 10 cubic centimeters. So therefore, the average grams of the vitamin C in each of those 10 cubic centimeters was 0.0145 grams. Final bit, we weighed out 0.29 grams of the unknown solid in 100 cubic centimeters. I split that into, I took 1/10 of that each time to 10 cubic centimeters. I've just worked out that on average, each of those 10 cubic centimeters contain 0.0145 grams of vitamin C. Thus, in that original 100 cubic centimeters of solution would be 10 times as much, or 0.145 grams of vitamin C. To get the percent vitamin C in the unknown solid, then 0.0145 grams of the vitamin C that I have determined via titration, divide that by the whole amount, 0.29 grams that I measured out, multiply it by 100, and my final answer, 50.0%. And believe it or not, I actually did these titrations to get these data. Like I said, a really, really nice one. Anyway, hope you enjoyed it. I'll be sending the link to this video to your teachers with the file that contains, the PDF file that contains certificates for you all. And remember what I said, we have a very big summer lab program, so I hope I'll see you back to do experiments. And also we have a work experience program, 1-week work experience, that is really for anybody doing a chemistry A-level who is going to go to university or go into a career for that matter, then some way that needs chemistry. So it's not just chemistry, chemical engineers, biochemists, but anything in the medical fields, you're doing your chemistry A-level because you need chemistry to go to medical school, pharmacy school, dental school, even vet school, and so on. So a week work experience in our labs over the summer would be a nice thing for pretty much anyone who's doing anything sciencey or medically to put on their UCAS, and hopefully have some fun with it as well. So hope to maybe hear from you all. s.g.bott@swansea.ac.uk. Bye-bye.